Yes, it's generally permissible to place 18 American wire gauge cables carrying 24 volts alternating current power in the same conduit as Category 5 network cables. However, some important considerations should be taken into account to mitigate potential electromagnetic interference, or EMI. 18 American wire gauge cables carrying 24 volts alternating current power typically do not generate significant EMI. Category 5 network cables are relatively resistant to EMI, especially when properly shielded and terminated. A 150-foot run is not particularly long, reducing the likelihood of excessive EMI. Maintaining a minimum separation of at least 3 inches between the power cables and network cables within the conduit is a good practice. Using cable trays or dividers to physically separate the cables and minimize crosstalk can also prove beneficial. Utilizing a metal conduit can provide additional shielding from EMI. Considering using a non-metallic conduit with EMI shielding properties might be useful as well. Always ensure proper termination and grounding of both the power cables and network cables. Avoid running the conduit parallel to fluorescent light fixtures or other sources of EMI. Test the network cables for performance before placing them in service. By following these guidelines, the risk of EMI can be minimized, thereby ensuring reliable operation of both the power and network cables in the same conduit. Delving deeper into these aspects will further clarify the safety and effectiveness of running both types of cables within the same conduit. We can begin by examining the potential sources and effects of electromagnetic interference. Electrical noise generated by power cables can sometimes interfere with the data signals transmitted through network cables. While 24 volts alternating current systems aren't typically high EMI producers, careful planning is still necessary. Factors that influence the severity of EMI include the current level in the power cables, the proximity of the cables to one another, the length of the parallel run, and the shielding effectiveness of the cables and conduit. In the case of current levels, while 24 volts alternating current itself is low voltage, the current flowing through the 18 American wire gauge cables can still induce EMI. The amount of current depends on the load connected to the 24 volts alternating current circuit. It's important to ensure that the current is within the rated capacity of the 18 American wire gauge wire and the circuit is properly protected by an appropriate fuse or circuit breaker. As for cable proximity, the closer the power and network cables are to each other, the greater the potential for EMI. Maintaining a physical separation of at least 3 inches helps reduce the coupling of electromagnetic fields. If physical separation is difficult to achieve due to space constraints within the conduit, consider using shielded network cables. Shielded cables have a conductive layer that helps block EMI from external sources. The length of the parallel run also matters. The longer the distance the power and network cables run parallel to each other, the more opportunity there is for EMI to accumulate. A 150-foot run is moderate in length, however, implementing preventative measures is still recommended. In situations where longer runs are necessary, consider breaking up the parallel run by routing the cables in different directions or using shorter conduit sections. Shielding effectiveness of the cables and conduit is crucial. Shielded network cables, as mentioned earlier, provide a significant degree of EMI protection. Metal conduits offer superior shielding compared to non-metallic conduits. If using a non-metallic conduit, look for options that include an internal metallic layer or are specifically designed to provide EMI shielding. Now let's focus on practical techniques for mitigating EMI. Physical separation is a primary method. As stated earlier, maintaining a minimum of 3 inches of separation is recommended. This can be achieved by carefully arranging the cables within the conduit during installation. Cable trays or dividers can be installed inside the conduit to create dedicated pathways for the power and network cables, ensuring consistent separation. Grounding and bonding are also essential for minimizing EMI and ensuring safety. Properly grounding the metal conduit, if used, creates a low impedance path for electromagnetic interference, diverting it away from the network cables. The grounding system should comply with local electrical codes and regulations. Bonding refers to connecting all metallic components of the electrical system together to create an electrically continuous path. This helps prevent voltage differences that can contribute to EMI. When terminating the power and network cables, ensure that the connectors are properly installed and grounded. Poorly terminated connectors can be a source of EMI and can also compromise the performance of the network. Testing is a proactive approach. Before placing the network cables into service, it's crucial to test them for performance. This can be done using a network cable tester, which verifies that the cables meet the required specifications for data transmission speed and signal integrity. Testing is especially important after the cables have been installed in the conduit, as the installation process can sometimes damage the cables or connectors. If the test results indicate that the network cables are not performing as expected, troubleshoot the installation to identify and correct any problems. Common causes of network cable problems include damaged cables, loose connectors, and excessive EMI. In addition to these techniques, consider the routing of the conduit itself. Avoid running the conduit parallel to known sources of EMI, such as fluorescent light fixtures, transformers, and large electrical motors. These devices can generate significant EMI that can interfere with network cables. If it's unavoidable to run the conduit near these sources, maintain as much distance as possible and consider using additional shielding. When selecting the type of conduit, metal conduit generally provides better EMI shielding compared to non-metallic conduit. Steel and aluminum conduits are commonly used for electrical wiring and offer good protection against EMI. Non-metallic conduits, such as PVC conduit, are less expensive and easier to install, but they do not provide the same level of EMI shielding. If using non-metallic conduit, consider using shielded network cables or incorporating other EMI mitigation techniques. It is also wise to select high-quality cables and connectors. The quality of the cables and connectors can significantly impact their performance and susceptibility to EMI. Choose Category 5 network cables that meet or exceed industry standards, such as those set by the Telecommunications Industry Association or the Electronic Industries Alliance. Look for cables and connectors that are specifically designed to provide good EMI performance. Consider using shielded connectors, which provide an additional layer of protection against EMI. Moreover, regular inspection and maintenance should be performed to help ensure that the installation continues to perform as expected over time. Inspect the conduit, cables, and connectors for any signs of damage or wear. Check the grounding system to ensure that it is still properly connected and functioning. Retest the network cables periodically to verify that they are still meeting performance specifications. If any problems are found, take corrective action promptly to prevent further degradation or potential safety hazards. Considering additional regulatory and safety aspects is also relevant. The installation of electrical wiring and network cabling should comply with all applicable local electrical codes and regulations. These codes are designed to ensure the safety of people and property and to prevent electrical hazards. In the United States, the National Electrical Code, or NEC, provides comprehensive guidelines for electrical installations. The NEC covers topics such as wiring methods, overcurrent protection, grounding, and bonding. Article 725 of the NEC covers Class 2 and Class 3 remote control, signaling, and power-limited circuits, which often include 24 volts alternating current control circuits. Article 800 of the NEC covers communication circuits, including network cabling. It's important to consult the latest edition of the NEC and to follow all applicable requirements. Ensure that all work is performed by qualified and licensed electricians or network cabling technicians. They have the knowledge and experience necessary to perform the installation safely and correctly. In summary, while it is possible to run 18 American wire gauge cables carrying 24 volts alternating current power in the same conduit as Category 5 network cables, it requires careful planning and implementation to minimize the risk of EMI. By following the guidelines outlined above, the likelihood of interference can be significantly reduced and the reliable operation of both the power and network cables can be ensured. The key takeaways are physical separation, proper grounding and bonding, and quality components. Also, routine testing and inspection, and adherence to electrical codes and regulations. With these measures in place, a safe and functional installation can be realized. One point to further address involves the specific application for the 24 volts alternating current power. Understanding the purpose of the 24 volts alternating current circuit can help refine the EMI mitigation strategy. For example, if the 24 volts alternating current is used to power a low current device such as a thermostat or a sensor, the potential for EMI is generally lower than if it's used to power a high current device. If the 24 volts alternating current is used for a critical application such as a fire alarm system or a security system, it's especially important to take extra precautions to ensure reliable operation. In these cases, consider using redundant cabling or separate conduits to provide backup in case of failure. Another important consideration is the environment in which the conduit is installed. If the conduit is located in an area with high levels of EMI, such as near industrial equipment or radio transmitters, it may be necessary to take additional steps to shield the cables. This could include using shielded conduit or wrapping the conduit with a layer of EMI shielding material. If the conduit is located in a damp or corrosive environment, it's important to use conduit and fittings that are rated for that environment. This will help protect the cables from damage and prevent electrical hazards. Furthermore, one should consider future expansion. When installing the conduit, anticipate future needs for additional power or network cables. It's often easier and more cost-effective to install a larger conduit than is currently needed than to have to add a separate conduit later. When selecting the size of the conduit, take into account the fill capacity of the conduit. The NEC specifies the maximum percentage of the conduit that can be filled with cables. This is to ensure that there is enough space for air to circulate and prevent the cables from overheating. In practical terms, the fill capacity depends on the type of conduit and the size and number of cables being installed. Consult the NEC or a qualified electrician to determine the appropriate conduit size. Finally, there are special considerations for underground conduits. If the conduit is to be installed underground, it's important to use conduit and fittings that are rated for direct burial. Direct burial conduit is designed to withstand the stresses of being buried in the ground, such as moisture, soil pressure, and temperature changes. It's also important to bury the conduit at the proper depth. The NEC specifies the minimum burial depth for different types of conduits and cables. This is to protect the conduit from damage from digging or other activities. When installing underground conduit, take precautions to prevent water from entering the conduit. This can include sealing the ends of the conduit and using waterproof connectors. Water inside the conduit can damage the cables and create electrical hazards. A related point is the impact of voltage drop. In long cable runs, voltage drop can become a significant concern. Voltage drop is the reduction in voltage that occurs as electricity flows through a cable. The amount of voltage drop depends on the length of the cable, the size of the wire, and the amount of current flowing through the cable. Excessive voltage drop can cause equipment to malfunction or fail to operate properly. In the case of the 24 volts alternating current circuit, it's important to calculate the voltage drop to ensure that the voltage at the load is within the acceptable range. The NEC provides guidelines for calculating voltage drop. If the voltage drop is too high, consider using a larger wire size or reducing the length of the cable run. Another factor to consider is harmonics. Harmonics are distortions in the alternating current waveform that can be caused by nonlinear loads such as electronic devices. Harmonics can cause a variety of problems, including overheating of equipment, increased energy consumption, and interference with other electrical systems. While 24 volts alternating current systems are not typically a major source of harmonics, it's still important to be aware of the potential for harmonic distortion. If harmonics are a concern, consider using harmonic filters to reduce the level of distortion. From a safety perspective, always de-energize circuits before working on them. Before installing or modifying any electrical wiring, always turn off the power to the circuit at the circuit breaker or fuse box. Use a voltage tester to verify that the circuit is de-energized before touching any wires or components. Follow lockout-tagout procedures to prevent the circuit from being accidentally re-energized while you are working on it. Wear appropriate personal protective equipment, or PPE, such as safety glasses and gloves when working with electrical wiring. Be aware of the potential hazards of working with electricity, such as electric shock and arc flash. In summary, successfully running 18 American wire gauge cables carrying 24 volts alternating current power in the same conduit as Category 5 network cables involves a comprehensive approach. We have covered EMI mitigation techniques such as physical separation, grounding and bonding, shielding, and cable quality. We have also highlighted the importance of adherence to electrical codes and regulations, consideration of the environment, feature expansion, voltage drop, harmonics, and safety practices. By paying attention to all of these details, we can create a safe, reliable, and efficient installation. Furthermore, the ongoing maintenance and periodic inspections will help ensure continued safe and effective operation for years to come. And by consulting with qualified professionals, electricians, and network cabling technicians, any potential issues can be proactively addressed.